My name is Harry Commin. I am an FPGA engineer at Enclustra, and this presentation is about FPGA-based vision systems. So just before I jump into the main topic, I'd just like to very quickly introduce who Enclustra are and what we do. So if you're already familiar with Enclustra, it's quite possibly because of our FPGA modules. We've been producing FPGA SOMs for 15 years. They're our most popular hardware product. Last year we sold more than 50,000 of them. Just recently we've launched this Andromeda module on the right, and coming up soon on our roadmap, we'll soon be releasing these little Pluto modules as well. But actually today's presentation is not about our modules, it's about another side of Enclustra's activities, which is our design services. So when I say design services, I mean that we don't only develop our own products, but we also work with external companies to help them to develop their products. So of course that can include the hardware aspects, but also we have plenty of engineers dedicated to putting designs into that hardware. So that means FPGA engineers like me, and also software engineers as well. So the idea behind the topic of today's presentation was really that, particularly in the last 3 or 4 years, we have seen quite an increase in interest from our design services customers in implementing vision systems in FPGAs. So today I just wanted to share some of our experiences and some of the lessons that we have learned through the years of doing those projects. So I think first of all, a really important question to ask is, why do we want to use an FPGA for a vision system? It's important to remember that FPGAs are quite expensive devices. Developing on them is relatively time-consuming and therefore expensive. So I think we should say up front that if your project can be delivered using a CPU-based system, then just use a CPU. It's cheaper, it's easier to develop, and you'll get to market quicker. So when do we want to use an FPGA? Well, usually that decision is driven by a high-performance requirement. So I think this picture on the right here gives a good example of that, because I think we can probably all agree that if this surgeon is operating on you, then you want him to see clearly with a high resolution, you want him to see smoothly with a good frame rate, and you definitely want him to have a low latency. Because if he is cutting through you with a surgical blade and he doesn't know where his hand is until half a second later, then you're going to have a big problem. So there are lots of other places where FPGAs also make sense. I think another hot topic at the moment is autonomous driving, where again we have this potentially very critical latency requirement, where it could literally be the difference between life or death if the system can react quickly enough to an emergency situation. So these are the kinds of high-performance applications that we're really thinking about with FPGA vision systems. So in this section, I'd like to talk a bit more about the specifics of the FPGA firmware, and in particular, how we take some vision algorithm that maybe we've developed in software, and then we want to deploy it in an FPGA. So when we do that, there are a number of different things that we need to think about. Unfortunately, today's presentation is extremely short, so I've had to reduce it down to just what I think are the 2 key topics to think about. So the first thing is, how do we take a frame-based software algorithm and convert it into a stream-based FPGA algorithm? And then secondly, and in my opinion by far the most importantly, is what types of mathematical rearrangements do we need to do in order to deploy our algorithm efficiently in the FPGA. So starting off with frame-based video processing versus stream-based, what do I mean by that? Well, first of all, if we look at a software that is CPU-based system, then typically in that type of system, we are able to buffer entire video frames of data in system memory. And that means that when we want to process this video data, we can very conveniently access that data in a completely arbitrary, random access 2D manner. So I'm showing an example here where in my high-level software language, I just need to index some two-dimensional array that will allow me to fetch those pixel values from memory. I can then process those values, modify them, and write them back into memory. And it doesn't matter if I want to process some other region of my frame. It's just as easy. Read, modify, write back. However, in the FPGA, the situation is significantly different. And the main reason for that is that we do not have a frame-based video processing system. We have a stream-based system. And what I mean by that is that if we imagine we have some video processing pipeline, like I've shown here, where we have multiple sequential video processing entities, then the unit of data that we are passing between those processing stages is not really whole frames. We have to think of it more that we are passing individual pixels, pixel by pixel between those stages. So the point here is that this data lane is typically 1 pixel wide. Okay, if we have a high throughput requirement, we may parallelize by a factor of 2 or 4 or 8, for example, but we are definitely not talking about passing entire frames of millions of pixels at a time. So this gives us really a fundamentally different starting point from which to develop our vision algorithms. So just to clarify what I mean, here I'm showing again the same example as before, where I'm saying we want to process this little 3 by 3 square of pixels in our frame, but now it's from the FPGA's perspective. So in this case, we are clocking through the raster scan pixel by pixel, and what I'm trying to show here is that when we reach time 5, so when we reach pixel number 5 in the raster scan, then we need to be careful that we don't forget the pixels 4 and 3, because they're inside the window that we want to process. And if this is a pixel by pixel system, then we need to do something to make sure those are remembered. So we have to explicitly insert some memory elements in our circuit, so a couple of flip-flops here, and then we can remember those pixels at the same time. And then we can proceed further through the frame. So we go all the way through the first line, through the second line, and into the third line. And then when we reach pixel number 45, we have again a similar situation to before, where we need to be careful that we don't forget the other pixel values that we want to process. So again, we have to add some more memory. So here I'm adding a line buffer so that I can remember those pixels from the previous line, and another line buffer to remember the pixels from the first line. But as long as we build a memory circuit like this in our FPGA, then we can process two-dimensional image data in the FPGA. So what kind of processing does this allow us to do? Well, for example, we can tap off all of these 9 pixel values in parallel and feed them into some computational unit. For example, here I've shown a convolution. That makes this whole circuit into a 2D FIR filter, which is very commonly used in image processing. But also that box could be a median calculation, and then this becomes a median filter that we use for denoising. And also this same circuit would be used in a convolutional neural network, so this type of circuit can also be important for AI-type applications as well. And just before I move on, I just want to highlight what I think is really the one key point to take away from this section about stream-based processing, is that horizontal offsets and vertical offsets are not the same in this system. Vertical offsets are very expensive because for each vertical pixel we need to span, we need an entire line buffer, whereas for each horizontal offset, we only need a very cheap flip-flop. So it is orders of magnitude more expensive to handle vertical offsets than horizontal offsets. And that's a challenge that we generally don't need to face in software. So moving on to the second optimization topic, and in my opinion, by far the most important, is mathematical rearrangement. So I'd like to just demonstrate this idea using one simple example, which is a Sobel operator. If you're not familiar with a Sobel operator, it's just a type of edge detector circuit that is often used in image processing. So the way this works is that we have some input frame coming in, we apply our Sobel operator, and at its output, it gives us this edge image with an estimate of the edge information in the frame. So in more detail, this works in 2 steps. So the first step is we have some input frame F coming in. That frame is then fed in parallel into these 2 processing branches. And in the first processing branch, we then convolve our frame F with this special 2-dimensional kernel GX. And that is specially designed to give us gradient estimates of the image intensity along the X direction of the input frame. And so in this second branch, we're basically doing the same thing, except we're transposing this kernel. So instead of getting the X gradient estimates, we're getting the Y gradient estimates. So then the final stage of this Sobel operator is to take that X component of the gradient vector, the Y component of the gradient vector, and calculate together their magnitude, the gradient magnitude. So we need some vector norm to do that. Usually a Euclidean norm gives the best results. But the question we want to ask now is, can we do something to make this thing more efficient to execute in an FPGA? And I think a good place to start looking here is at those numbers in that matrix. There seems to be a lot of structure there. There's a lot of symmetry. Is there some way that we can exploit that structure in order to reduce the number of computations that we do in the FPGA? The answer, of course, is absolutely yes. And the first trick to notice here is that that 2-dimensional matrix actually can be written as the product of 2 one-dimensional vectors. So this is something we call a decomposable kernel. And just to write it slightly differently, we can put a convolution operator in the middle there. It means mathematically the same thing. But now this shows a very powerful result, which is that instead of doing this quite expensive 2-dimensional convolution, we can now do mathematically exactly the same thing by doing 2 very cheap 1-dimensional convolutions. So the computational cost of this has gone from being 7 times 7, 49 multiply accumulates per output pixel, to now being 7 plus 7, 14 multiply accumulates per output pixel. So just by thinking a bit, we have reduced our computational complexity by a ratio of 3.5 to 1. So it's a huge, huge improvement. I think that the next thing that's interesting to note about this is that this convolution operator is a linear operation. So we can actually swap the orders of these convolutions. Mathematically, it makes no difference at all which way we do those. So let's just arbitrarily choose to do them this way and then shift those in to replace the expensive 2-dimensional convolution, and now we get a system that looks like this. So this should work great, right? Well, actually, it turns out, no, that was not the right way to do those 2 convolutions. Again, this comes back to mathematical rearrangement. We had mathematically 2 equivalent ways of doing something, so we have to analyze each choice and choose the one that makes more sense in hardware. And this way does not make sense. We really want to swap them around this way. And the reason that we want to do it this way comes back to what I said at the start of this presentation, was that vertical offsets are expensive to process in a stream-based system. Horizontal offsets are cheap. And the point of doing it this way around is that only in this configuration do we have the same input data going into both of these expensive vertical convolutions. So in this case, it's the same data getting buffered in those expensive line buffers, so the same buffers can be shared between the 2. So again, just by thinking a bit, we have halved the memory requirement of our component. So are we finished with our optimization? Well, no, we're not, because again, just look at these numbers. There's still so much structure here. There's so much symmetry. And in fact, all 4 of these 1-dimensional vectors are either symmetric or anti-symmetric. So this is a symmetric vector because it's a mirror image of itself, and this is an anti-symmetric vector because it's a mirror image but with a negative sign in it. So this is very well known in the world of digital signal processing, how to optimize this type of filter. So I'm just summarizing it here. On the left, I've got the naive, unoptimized implementation where we have 7 multiply adds implementing the 7 coefficients. And I'm just showing that due to the symmetry, we can take these symmetrical pairs and actually implement them using just 1 multiply adder, but with a pre-add as well. In this case, actually, I'm showing an anti-symmetric filter, so it's a pre-subtract instead of a pre-add. But we can do the same here and the same here. So we roughly halve, again, the number of multiply accumulates. We've gone from 7 down to 4. And actually, we're still not finished, because you may notice, for example, that this coefficient is 0. So obviously, multiplication by 0 doesn't do anything. So we're not going to spend a valuable multiplier to do that. So we can just remove that from our diagram. And in fact, we can keep going, because multiplication by 1 doesn't really need a multiplier either. It's just a wire. And 4 as well. 4 is a power of 2, so it requires precisely 0 FPGA logic to implement. It's, again, just wires. And even multiplication by 5 is not much more complicated. That's times 4 plus times 1. So you actually only need 1 adder to implement a multiplication by 5. So we have a couple of options here. It's a trade-off. It depends on which resource we're really trying to optimize in our system. If we have lots of available DSP slices in our FPGA, then we might decide to do these computations in DSP slices. Or if we're worried about using all of our DSP slices, then we could reduce their utilization by moving these adders into FPGA fabric. So why did we bother with all of this optimization? Well, here's just a very quick summary of what we achieved. So first of all, here we have the original, naive, completely unoptimized, 2-dimensional convolution version, where it turns out we needed 84 DSP slices and 1,000 LUTs. We've got +3 DSPs for all of these, because all of the implementations use the same RGB to grayscale conversion. But then, just by doing our bit of mathematical rearrangement, we were able to either optimize for LUTs, so that we can reduce the number of LUTs from 1,000 to 500, and at the same time reduce the DSPs from 84 down to 14. Or if we really want to aggressively optimize the number of DSP slices, then we can force that all the way down to 0 at the expense of 200 more lookup tables. So just by doing some mathematical rearrangement, we've given ourselves 2 options, some flexibility, but both much better than the unoptimized version. Okay, so in this next section, I'd like to talk a bit more about bringing the whole vision system together, bringing it up and getting it working efficiently and effectively. So what I'm talking about here is a scenario something like this, where we've done all of our development, we've produced our hardware, our FPGA firmware, and our software. And on day 1 of bring up, we switch on our camera, we turn on our screen, and nothing happens. And we say, oh, damn, like what happened? This is supposed to work. What could possibly have gone wrong? And we think of it and we say, well, there was quite a bit of new development we did here. I mean, we have manufactured completely new hardware. We've written completely new FPGA firmware. The bus infrastructure used components that we're familiar with, but we've connected them together in a totally new way for this new project. And of course, we've written brand new drivers for our brand new components in the FPGA. And of course, our software test application is specific and new for this project. And in addition to all those new things, there's actually a whole bunch of things that we're just using for the first time. So maybe this model of camera, we haven't used this one before, and therefore the interface IP for that camera inside the FPGA, we've never used that before, and maybe the same for the display. We haven't used that or its IP before, and therefore we haven't used its drivers before. So there's actually quite a lot that could possibly have gone wrong here. How do we go about solving this problem? Well, it may seem quite easy for the project manager to just push all the developers into a room and lock the door and say nobody's coming out until you find the answer. But a situation like that normally goes something like this. So Maybe, for example, it's the application software team who first detect the problem because they were the first to run the whole system. And they say, well, all of our software is passing its unit tests. We can't see anything wrong in what we have done. Maybe there's something in the Linux, maybe the device drivers or the device tree could have a problem, so they consult the Linux expert. He checks what he did, and he says, no, I've checked everything. I'm communicating correctly with the FPGA. Maybe there's a problem on the FPGA firmware side. The FPGA firmware team then look at what they did, and they say, well, we've test benched everything that we did. It all works perfectly. But then when we integrate it with the third-party IP, things seem to start going wrong. So maybe it's the third-party IP. So you then reach out to the IP vendor and say, could it be something here? Of course, they say, no, our IP is well tested. But maybe the input signal coming from the camera, if that's garbage, then anything could happen. So you speak to the camera vendor, and of course the camera vendor says, no, our camera has been used in lots of projects with no problems. You've probably integrated it wrong in your system or wrong in your hardware. So then it comes back to the system designer, who then consults with the hardware team and says, okay, let's triple check our schematics and really make sure everything's perfect. And then maybe after all of this effort, they find some extremely tiny bug, like there's one differential pair that's been connected the wrong way around. So 99% of all of this effort and all of this checking was wasted by people who were just never involved in this problem. So this is kind of a classic needle in a haystack problem where there's this little tiny bug and it's lost in this enormous system, this enormous amount of data that you have to crawl through to try and find this bug. So what can we do to try and improve this situation? Well, obviously in an ideal world, we would just say, let's not have any bugs. Unfortunately, I think we all know that that's simply not realistic. So let's be more realistic. How can we systematically try to reduce the number of bugs that we see in our system? So of course, the first step, follow a clean design process. And this first point just seems so obvious that I'm almost embarrassed to say it, but it really can be overlooked. Think before coding. And I mean really, really think. So at Enclustra, our rule of thumb is that 90% of all of our documentation for the whole system design should be completed before the implementation work starts. And the thought process for doing that is that if you can't write down exactly what you're about to do, then you're not ready to do it yet. And you need to go back to the design and really clarify what it is that you don't know. Then the other 3 points here are really about avoiding regression bugs. So of course your software should have unit tests, your FPGA firmware should have self-checking test benches, and ideally there should be a continuous integration system for running automated builds, because you want to be absolutely confident that when you change something small or add a small feature, you don't break something that was previously working. Then the next point here is to reuse existing code. Develop your own code libraries, maintain your own code libraries. Of course, the more you use them, the more you trust them, the better quality you get. A secondary option here is to buy off-the-shelf IP, but there can, of course, be risk involved in that because the quality of the results that you'll get from the IP will depend on the quality of the IP, and it's not always easy to know what that quality is until after you've bought it. Another one that seems obvious, but I think can be underestimated, is hire very good developers. The statistics we hear from within the industry are that excellent developers are not just 20 or 30% more productive than an ordinary developer, but more like multiples, so 2 times or 3 times more productive, and they are certainly not being paid 2 times or 3 times as much. So it's just simple mathematics. For best value for money, get good developers in the project. Last point here is slower is faster. What we mean by that is when things start to go wrong, do not panic and start rushing things, because as soon as things start to get rushed, that's when we start to throw away all of this nice clean design process. So developers start coding without thinking, they don't verify things correctly, Code reviews don't happen anymore, and it's really at this time is exactly when we need those things the most. So when things start to go wrong, accept up front that there's going to need to be a time investment in getting this fixed, and don't take shortcuts because they tend to lead to longer paths in the end. So the second half of this needle haystack problem, of course, is the haystack. How can we break down this enormous system, this enormous amount of data we need to look through to find where the bug is? And really, we think that the key here is to design for bring up. And so that means that from the design phase onwards, build in diagnostics into your system. So that means proper error handling in software, proper error flags and status reporting from firmware components, and log files so that you can track back through and find what threw an error first. It also means breaking up the processing chain to some extent so that you can localize this error checking. So you can input test sources to a local part of the design and get status that points to that part of the design. So that when an error flag is thrown, you can pinpoint where the problem is in the system. And the last point here is if you have a particularly complex design or there's a particular part of the system that is less trusted or less known, then separate that into its own proof of concept. It's much easier to gain trust in a small part of the system and then integrate it into the larger system rather than trying to throw everything together all in one go with many unknowns at the same time. This is basically saying the same thing, so I'll skip past. And that's basically all we have time for. So just to quickly summarize, we looked at FPGA-based vision systems where we're particularly talking about high performance, meaning high resolutions, high frame rates, low latencies. We looked a bit at how to optimize our algorithms to go into an FPGA, and then at the end we talked a bit about how to bring up the whole system in an efficient manner. This last slide is just from our marketing to say, always please don't hesitate to get in touch if you're interested in any of the things that we do. Our website has lots of free resources on it, white papers and reference designs and all sorts of things to look at. I will be here at our booth for the rest of today, so if you have any questions for me, then please come and talk to me. But otherwise, thank you very much for listening.